Okay, last problem in this very long practice exam. So this is another more or less standard problem where we're going to start with a mechanism, only a three-step mechanism this time. But it's a little bit different than the others because it asks you to, first of all, of course, write out all the rate equations, but then it asks you to actually solve some of those rate equations. Find the integrated rate expression for A as a function of time, for example. Then it asks you to simplify, to simplify some of the rate equations using the steady state approximation. So that's the same kind of thing that we've done before. That should be okay. But then it asks you to find integrated rate expressions for two of the products as well, C and D. And then it asks you some questions about the results at the end of all that. So it's similar to one of the standard problems above, but it's a little bit more complicated. It asks you to go a little bit further. It's a good exercise to see if we understand how all that works. Over here, I've written the problem out in a little bit more graphic form, so it's a little bit easier to follow what we're supposed to be doing. First of all, I rewrote the mechanism so that it shows a little bit better what it's actually doing, right? There's some initial reactant A, that turns into a B, and then the B can go to either C or D. In other words, it's the branched mechanism that we talked about before, but with a little pre-step in front of it. So we don't start with B and then split into C and D. We start with A, which then creates B and then gets split. And the question is there anything new that shows up because this is a slightly more complicated mechanism than the branched mechanism above? The rest of this is just summarizing everything we have to do, so we'll go through that bit by bit. First thing we have to do is write the rate equations. So let me copy this down. And we'll do that first. And let me clean up this mess a little bit here. All right. So write the rate equations. We should be good at this by now. dA dt is equal to minus, from this first step, K1 times A. dB dt is going to be the only one with any real complexity, right? It's going to be plus K1 times A, because it's a product, and then minus K2 times B and minus K3 times B. And let's just rewrite that a little bit. So that's K1 times A minus K2 plus K3 times B, right? So B goes away with the sum of the two rate constants because there's two channels by which it can disappear. And that's going to happen in every case where you've got branched mechanisms like this. Happened when we talked about branch mechanisms earlier too. Then dC dt is equal to just K2 times B, and dd dt is equal to K3 times B. B is an intermediate here, right? It's not, the overall reaction is A goes to C or A goes to D. And so when we do the steady state approximation, we're going to set this rate equal to 0, and that will allow us to eliminate these intermediate concentrations in the rate laws for C and D. So that's the overall plan, but the first thing the problem asks us to do is solve for how A varies with time. And notice that we've got a nice closed differential equation. In fact, it's a first order differential equation for A by itself because A goes away. All these steps are irreversible, so A goes away independent of whatever is going on over here. We don't even have to, as far as A is concerned, it doesn't even know that all this stuff's happening over here. So this set of relationships here, let me eliminate all this junk again. This set of relationships is part A. For part B, we have to solve. And since it's a first order relationship for A, we already know what the solution is. It's A is equal to A0 e to the minus k1t. And so that, I think, solves part B all by itself, yes. Then part C is to use the steady state approximation. That means set dB dt equal to 0. That means that this relationship right here is equal to 0. So that's equal to 0, approximately equal to 0. It is an approximation after all. A is a majority species, B is the intermediate. We want to solve for B, so that's B is equal to K1 over K2 plus K3 times A. Okay, now we have the steady state relationship that allows us to eliminate the intermediate. What we want to do next, in the next part of the problem, is use that relationship to find useful rate equations for C and D, which we can then solve to find how C and D change with time. So to do that, dC dt is equal to K2 times B, which is now K1 over K2 plus K3 times A. But A we have solved for before, so this is K1, K2, let me write this a little better. K1, K2 over K2 plus K3 times A0 e to the minus K1t. And now to solve this differential equation, right, we have nothing but time on this side, things that depend on time on this side, and we have the time derivative on this side. So if we just take the integral of both sides, integral from 0 to t of dc dt, that has to equal all these constants in front times the integral from 0 to t of e to the minus k1t dt. And now we just have to do the integrals. Doing the integral of a time derivative like this just means that we get the actual value of c evaluated between 0 and t. That has to equal K1, K2 over K2 plus K3 times A0, and now the integral of this is e to the minus K1t over minus K1 evaluated between 0 and t. And so, evaluating on both sides again, we get c at time t minus c at time 0, which is just c0, but that's a 0, right? There is no c at time 0 to start with. And that is equal to K1, K2 over K2 plus K3 times A0. And now evaluate this guy at time t, so that's e to the minus K1t over minus K1. And then evaluated at time 0, so that's minus a 1 over minus K1. And that means that C is equal to K1, K2 over K2 plus K3 times A0, 1 minus e to the minus K1t over K1. The K1s cancel, and we get that C is equal to K2 over K2 plus K3 times A0 times 1 minus e to the minus K1t. Now, doing the same thing for D, you can see we're going to get exactly the same answer, except that there should be a K3 wherever there's a K2 here, and so we're going to have D is equal to K3 over K2 plus K3 times A0 times 1 minus e to the minus K1t. All right, so there are our two integrated rate equations in the steady state approximation for C and D. Before we go on, which we're going to look at branching ratios in the next step, let's plot that a little bit. First of all, A goes down exponentially like a first order reaction as always, And then when C and D rise up, what's happening? Well, as time goes to infinity, that term is going to go to 0, right? That term is going to go to 0. That means all we're going to get is just these first two terms when time goes to infinity. And notice, this plus this is equal to 1. So this is a fraction of the amount of A0 that we started with. And that's a fraction of the amount that we started with. So this is really answering the last part of the question already. These two curves, as time goes to infinity, have to add up to the total amount of A0 that we started with, and that means that the fraction of A0 of C that we end up with is equal to just K2. This is at time infinity over K2 plus K3 times the initial amount of A0, and the same for D infinity, K3 over K2 plus K3 times the amount that we started with. If we take the ratio between those two, that's just equal to K3 over K2, which is exactly the same law that we got earlier for the branched mechanism alone, the simple branched mechanism. Namely, that the amount of C that you get and the amount of D that you get, the ratio of those two is controlled by the ratio, well, is the same thing, in fact, as the ratio of those two rate constants. And that's why it's called the branching ratio. It tells you how much goes in one direction and how much goes in the other direction. And I think that is the end of this problem. And so I hope everyone does well on the actual final coming up on Wednesday. I hope if you have questions, you'll email me.